everyone. We, the team of energy prodigies, are presenting our project. So, our prototype includes as the problem statement provided by the Ministry of Power, that is, developing an AI-powered energy management system for a commercial facility to optimize the energy consumption. Now, let us discuss what is the first step included. We will first collect the real-time load data from our commercial facility, and we have considered the commercial facility as our own university campus, and we will collect the real-time load data through our various sensors located in our hardware model. Now, as we can see, this is our hardware model. This is our voltage sensor, which will monitor the voltage. This right here is our current sensor, which will monitor the current. This is our converter to convert the AC to DC. Now, all the load data will be stored in our microcontroller Arduino Uno. Now, let us consider this load box that we have considered as an equivalent university campus. We have divided the entire campus into 4 zones. Zone 1, Zone 2, Zone 3 and Zone 4. All these zones represents the different zone of a university campus. That is, for example, the faculty room, the seminar hall, the practical rooms and the theory classes. All these different loads will give us different loads of the day. Now, from the Arduino Uno, a serial connection has been made with our Node MCU module to make our prototype completely Wi-Fi based. So, from the Wi-Fi module, the data will be shown in our monitor, in our device continuously. 24 hours data will be shown, as well as it can be shown in any Wi-Fi connected device. As we can see, the energy, the power. As we scroll down, we can see the current, the power factor, as well as the reactive power. The voltage data also can be shown. Otherwise, we can also view all these parameters in any electrical connected devices. That is our mobile phone. Any mobile phone we can see, as we can see, the monitor can be done. So the complete system becomes completely Wi-Fi based and smart metering from any part of location at any time of the day. Now, as we could see, after monitoring all the electrical parameters on our devices, we have used the technology of artificial intelligence to minimize the energy consumption to the fullest. Now, how we have done it? We have used the strategy of demand response management. That is, the loads which we are getting from the 4 zones of our university according to the availability of the renewable energy source and the grid power. We will shift the load to a particular region where the energy consumption will be mostly from the renewable source and not from the general grid. By this, the consumers will be able to consume the load as much as possible from the renewable sources. Thus, there is a scope of cost savings. So, the demand response management strategy and the whole AI process will be explained further and more proficiently by my teammate Shobhan.
Hi everyone, I'm going to explain how I implemented AI technology for the demand response management and energy optimization strategy. So first of all, as my teammate said, we have just categorized different zonal loads into 4 types, which is zone 1, zone 2 and zone 3 and zone 4. And we have 2 categories of them, which is controllable and uncontrollable. So uncontrollable loads are considered to be high priority because there are many constraints we have involved around it. So we have to adjust it before any other load, any other uncontrollable load is adjusted. So first of all, let's know about how the AI technology is working. So for optimal decision making, we should know about what's the future. And so that analogy is applied over here. So we have to know what is the future. So future is what is the forecasting. So we implemented this forecasting, and we can see this is demand, total demand is one thing which we can forecast, and we can estimate what will be the maximum demand for the next day. We can use the grid supply and renewable supply availability as well, because we have to make it simple, we haven't considered renewable and grid supply uh, variables. So we have just considered it's pretty constant. So let us drive through what we have done. So first of all, we have done just data frame manipulation and pre-processing to adjust our data according to the way it's suitable for our model training. So yeah, you can see over here we have the graph of the total demand. You can see the blue line, and the total demand is peaking around this time, and it's not good. It's not good. And we have zone 3 and zone 4 over here. You can see the load pattern consumption, and I can say this is not optimal pattern of consumption. So we're just going to readjust into an optimal pattern. So yeah, so you can analyze that how the demand is total demand is varying with hourly basis. So yeah, we have to use this AD Fuller test, and we have used the SADIMAX model. And SADIMAX is a statistical machine learning model and a library, we can say. We have used this because to forecast, and and SADIMAX is utilized because we have a seasonal trend. Yeah, you can see this seasonal trend. It's going to repeat next after a certain amount of hours in the next day. So we have considered it to be SADIMAX because other libraries also are present. They are not giving a, they are just rendering a constant, forecast. So I think SADIMAX is optimal for this case, and we just fit the, data, total demand data with the model, and you can see the log likelihood, and the log likelihood is pretty low, and that gives you a intuition that it's pretty, the forecast will be pretty accurate. And so we have just manipulated, generated the next day timeline, what will be the timeline for the next day, and then we have predicted for the next day's total demand consumption, and this is the predicted value. And you can see this predicted predicted consumption pattern, and it's pretty accurate based on the tomorrows. And we can see some of the discrepancies are there. This can be adjusted by normalizing it. We'll show you how we did it. So yeah, we have just done with the prediction or forecasting of new Sarima model, and we have used the autoregressive model properly, and we are just going to use it again for the two loads I mentioned. This is uncontrollable and controllable, because zone 2 and zone 1 load are pretty constant. And uh, you can analyze over here. Let me show you. Yeah, so here you can see these are the zone 3 and zone 4. In between them, there's some load present, right? And these loads are pretty constant. And these loads are not switching off and on with any interval of period. So if we adjust that to some other time zone or timestamp, it would be extending the window. And in a commercial unit, we have a window constraint, and we have to finish up the work within that time period. So we have to follow that window. So for following that window, we just analyze that there are two things which can be adjusted, and we can fit into the window properly, and the time limit will be within that window. So we have just took zone 3 and zone 4 because this is high amount of load demand. And you can see this is zero point 0.3 and 0.8, and zone 4 is actually a seminar, and zone 3 are the 3 lab classes, and lab classes are pretty high demanding loads, and seminar is obviously high demanding load, and it has some constraints as well, as I discussed earlier. So yeah, it's having a lot of participants and guests, and their constraints is also there. We cannot shift to an arbitrary time period, because there are some obviously comfortability is also a factor. So we have just forecasted these two consumption patterns for the next day, as we did for the total demand, and we just did that 80 Fuller test, and we have implemented the Celimax model, and these are the seasonal and ordered. Um, you can see, and let me show you the log likelihood. It's pretty good. Log likelihood for zone 3, it's 11. I think that's okay for uh, decent amount of accuracy, and we have log likelihood 10. It's also pretty fine. uh, I think it's good amount of accuracy is also there. And as we did for the earlier total demand, we did for the same. We have rendered new timeline, and we have predicted for the new timeline, that is the next day, and we have the prediction, and this is the predicted graph. You can see it's pretty accurate, and with respect to the yesterday's data, and you can infer that we have a pretty accurate model. And there are also some discrepancies as well, as you can see, and that can be normalized. So yeah, and we are now here with the most interesting part of our you know model, and which is the load shifting, the demand response management, or the energy optimization. So yeah, we have forecasted three parameters, which is forecasted consumption, total demand, and forecasted zone 4 and zone 3. We have concatenated all this data which we have predicted into a singular data frame, and this is you know the load curve, which will be occurring tomorrow based on today's data. So you can see, we have to shift it in an optimal way to reduce this peak and to reduce the energy consumption cost. So yeah, how should we achieve this this optimal load consumption pattern? So for optimal load consumption pattern, we have to shift the load in a you know proper way, so that we have to fulfill the comfortability issue, and as well as the cost also minimized. So for these two parameters, what can we do is that we utilize this concept, which is the first of all the compatibility, or our priority. So the first priority, as I said earlier, that the forecast is zone 3. Zone 3 is a seminar, and zone 4 is a seminar, sorry, and zone 4 withholds many constraints, like there can be a guest, there will be a lot of students, and you have to fit it into this window, so that everyone has a common timing to arrive at that place. So for that, what we can use, you cannot shift this after the work hour or somewhere around that. That can minimize the cost much more, but you have to use an intelligent way as well. So for that intelligent way, we have considered that in the beginning of the work day, we can just shift it to make it available for everyone to attend, and then we can just manipulate this load, because load 3, the zone 3 loads, because these are lab classes, and we can just lab classes are for short duration of time, and we can just fit it properly. So yeah, so that analogy we used, and these are the implementation. First of all, as I said, that there are many discrepancies in the data, and this is fluctuating, and this is not good. So we have just normalized this fluctuating portions of the data. And first of all, what we did is that we just normalized it, and we just declipped what was clipping over here. We just subtracted this zone 3 and zone 4, and we just declipped it, and you can see these are all the constant loads, and this can be shifted because these are all constant loads. And for running a commercial unit, you have to have this load running for a constant period of time within the window. So yeah, now we will shift zone 4 and zone 3, and first of all, we will normalize this. We have normalized this all the discrepancies, as you can see over here, and after normalizing it, we have this two two zones, which is 4 and 3, and we have to shift in an optimal way. So what I used is that I thought that let's shift this to the right, left, and this three to the right, so that what happens is that we can adjust these three classes within the time frame, and the fourth one also have fulfilled all the constraints. But if I do it other way around, then obviously this zone 4, this is the biggest load demand, will be shifted more rightwards. And if it shifts more rightwards, the energy consumption will be minimized for a certain period of time because it's falling under zero point 0.8 per unit. But the thing is that you have to extend the window, and nobody wants to attend class or anything institution after hours, so we have to fulfill that issue as well. So we adjusted the load according to the criteria, and we can see this is a rendered optimized load consumption pattern. So we have shifted this green one, this is zone 4, to the right, and we have to face some point 1.2 per unit, because yeah, obviously there are many local minimas present over there. That's just stated, this was the global minima, but we have to use the local minima for our comfortability constraint as well. We have to fulfill that as well. So we have utilized this, use this minima and local minima, and I think this is the most optimal according to our constraint. And then we have shifted this high priority load to the left, and controllable load shifted right. And this, as you can see, this orange loads are shifted right, and we have adjusted in the time frame. This is the red one is the time frame, and yeah, it's pretty done successfully. And we have rendered this into a data frame, and we can just compare what we have before optimization. As you can see, 1.6, yeah, pretty high, and we can have this 1.2, yeah, for a short duration of time. And yeah, we have pretty minimized load consumption, as well as cost has been minimized successfully. Thank you.